Hello everyone, in this video I'm going to talk about integral windup and some methods we can use to solve this problem. Many control systems can be understood based on linear theory, but not all control systems are linear. Some nonlinear effects must be accounted for when designing a PID controller. The windup problem is related to the integral error of a controller. When we are dealing with a nonlinear system, we need to take into consideration the physical limits of the actuators of the plant. When we're controlling an actuator that has a physical limit in a closed loop using a PID controller, when and if the actuator reaches that limit, the integral part of the PID will start to accumulate, creating large values and thus making it harder to get the control error to zero. Let's talk about this. The source of the issue, as I already stated, is the limits. Physical limits of actuators have a negative effect on the PID controller. Here in the left graph I have an ideal actuator, and here on the right I'm going to draw a more real actuator. So the response of the actuator should be something like this. When we reach that limit here, we could say this part starts to be the windup. Let me use the model for a pendulum on a cart to explain this a little bit further. In this model, the input signal is a force that acts directly on the cart, and the output signal that I'm interested in controlling is the position of the tip of the pendulum here. Both the cart and the pendulum have the same mass. When the external force acts on the cart, it's going to make it move forward, and as we can see here, the pendulum will start to lag behind, but we want to control this. So our system looks something more like this. The pendulum is not lagging as much, and we avoid the limit of the revolute joint so we don't get the integral windup. If we were to simulate both carts, we would see something like this. On the left, we have the cart that doesn't have any type of anti-windup, and we can see the response of the graph has an overshoot. On the right, we see the cart that has anti-windup built in, and theoretically we should get a response similar to what is shown in the graph. The question now is, how do we implement integral anti-windup in our PID controller? First, we need to choose one of the many anti-windup methods. For example, back calculation anti-windup, the observer approach, the conditioning technique, or the incremental algorithm. For the pendulum on a cart model that I showed you previously, I used back calculation anti-windup to obtain my results, as it appears to be one of the simplest ways to control the windup problem. The back calculation anti-windup technique makes use of a feedback loop that connects directly to the PID controller. This is to quote-unquote discharge the integral part of the PID controller when this controller reaches an established threshold for acceptable saturation levels, and it enters a nonlinear behavior. The implementation for this method of anti-windup control is shown in the following diagram. Here is the block diagram that I used for the implementation of the back calculation anti-windup control in my pendulum on a cart model. Here it's my input signal. Over here it's the process I want to control. Here it's my PID controller. And this is the saturation level I established. As you can see, the saturation level sums here and goes back into my PID controller right on the integral part. This feedback into the integral part of my controller is what allows me to control the acceptable saturation levels. This prevents my process from entering a nonlinear behavior and makes the control of the system much better. as we can see here. This shows what the no windup control graph looks like and how our windup controlled graph looks like. It's obvious the best option is to always have windup control, especially if we are talking about back calculation on the windup, as it is really easy to implement and it gives us much better results. Thank you.